Excell for Raman spectroscopy, surface enhanced Raman spectroscopy, infrared spectroscopy, and mid-IR laser spectroscopy. So we'll start with the absorption of methylene blue on silver nanoparticles. Please start recording.
It's already recording.
Thank you. Okay, first, a little bit of theory and experimental concepts. Raman is a light scattering event. It provides information on the identity of compounds, that is, characterization, on and the specific bonds of atoms or groups of atoms in molecules. Raman spectroscopy also provides information on intermolecular interactions in mixtures. Since normal or conventional Raman spectroscopy is a very weak phenomenon, surface-enhanced Raman spectroscopy improves the intensity of the Raman signals, making it comparable to infrared spectroscopy or IRS. On my left of the screen is a series of measurements on the absorption of 10 to the 4th molar methylene blue, which is a dye, on silver nanoparticles. We're going to pause and eventually to show you how these spectra are arranged in sequential form. But you can see that we're measuring from about 1 microliter of 10 to the minus 4 molar methylene blue all the way to 40 microliters of 10 to the minus 4 molar methylene blue. There are 3 absorption models, Langmuir, Freundlich, and Fumpkin. I did not include Fumpkin in this presentation, but that's another alternative. Langmuir relates the absorption of molecules onto a solid surface with the concentration of a medium over the surface at a constant temperature. It doesn't require to have equilibrium, and it favors monocoating of the surface. On the other hand, Freundlich relates the concentration of a solute on the surface of an absorbent, a surface absorbent, with the concentration of the solute in the liquid in contact with the surface. There are the 2 equations on the left for Langmuir. Theta equals K times C, where capital C is the concentration of the analyte divided by 1 plus K times C. K is the absorption constant, and that equation can be linearized by dividing by 1 over the concentration on both sides of the equation, and you get the concentration divided by theta is equal to 1 over alpha, which is the intercept on the linear part of the absorption process, plus beta over alpha times C, and beta over alpha is the slope la pendiente, and as soon as you get the intercept on the y-axis, which is 1 over alpha, and you have the slope, which is beta over alpha, then you can calculate alpha and beta from the linear section of the absorption process. On the other hand, Freundlich requires equilibrium, and that's labeled as theta equals K, the absorption constant, multiplied by the concentrations labeled C sub I, and it's comma EQ, which means that it requires equilibrium elevated to the nth power. Here, K and N are the two constants that you want to determine. That equation can be linearized very efficiently by taking the log base 10 at both sides of the equation, and you get log theta is equal n log Ci sub equilibrium plus log K. Again, log K is the intercept in which you can calculate K, and N is the slope. And as soon as you calculate log of N, well, if you represent this equation, you get the slope, which is N, and you get the intercept, which is log of K. I didn't have time to convert this into English, but here are the band intensities represented in terms of intensity slash counts. And the purpose of this work, this seminar, this webinar, is that you understand that the way of representing, the standard way of representing the y and x axis is that you have the property divided by the unit. So that's why it has a slash over here. Methylene volume divided by microliters. And then on the x-axis, you have numbers, which of course represent microliters. So this is a standard way of representing. An alternative to this is to, after the methylene volume, place microliters in parentheses. But that's not the standard way. The preferred way is this. On the y-axis, intensity divided by counts. So the numbers here doesn't have dimensions because the axis should not have dimensions. Calibration curves, and this is in Spanish, just because, again, I took this from a report, but this is good representation of the absorption process. When you do your calibration, you have a linear segment. You can have a second linear segment for very high concentration of the analyte. And again, after that, you have a plateau, a flat part which has a slope of 0, pendiente de cero. In SIRS, you could even have this part extended downwards, which means that the silver nanoparticle surfaces have been saturated with your analyte, in this case, methylene blue, and then SIRS doesn't take effect any longer, and you get the Raman from the bulk of the analyte. So you're required to have single or monocodes or single codes. And this is a lousy calibration curve, but I wanted to add it in to see what we can do with it, because there's a lot that we can do with the calibration curves. In here, on the right, we have theta. We have, in the y-axis, we have counts. On the x-axis, we have concentrations. And here, you see, I represented C sub I at equilibrium, parentheses, in grams per liter. Here are the experimental data for the absorption of methylene blue onto silver nanoparticles. And this is a spectrum that you saw before. And it's great. I left a glitch right here. I left part of a parenthesis. Nobody's perfect, okay? But you have Raman shift, backslash, slash, wave numbers, that is centimeters elevated to the -1, and you have the full spectrum from 200 wave numbers all the way to 1700 wave numbers. And the aliquots that were added sequentially to 1 milliliter of silver, a suspension of silver nanoparticles that goes from 1 microliter all the way to 40 microliters. These are the tentative band assignment which everybody should look up and assign your spectrum or spectra with the bands that are shown in the literature. Please refrain from calling these theoretical assignments. Almost no one does theoretical assignment except in our group. I hope that Michael will do the theoretical assignment using Gaussian. When you use Gaussian, the Gaussian program, you're basically doing theoretical computations. So you can calculate the Raman and infrared spectra as Michael did with the picolinic acid for Tatiana Serrano's work. And here are the spectra with the assignments. Search spectra with vibrational band assignments. Here is how methylene blue looks like, and let's go into more detail. Sometimes you're required to correct for the baseline. Be careful when you do that. It's not clear that you want to do that every time, only if you have to. And remember, when you do chemometrics or multivariate analysis, the program partial least squares actually does the baseline correction. So don't bother with doing baseline correction. Sometimes it messes up the spectra, as you will see in this case. But here, what they did, and these are all experimental points, okay? And they're very close together, so close together that when you integrate over a band, you don't have to use trapezoidal rule, you don't have to use Simpson's rule, you don't have to use Newton's rule. You only have to add the cells in an Excel file, and I'll show you how to do that. But here, what I suggested my student is that they connect the, the farthest point on the left of the spectrum, and this is a part of the spectrum, which goes from 400 weight number all the way to 600 weight number, which is the most intense band of methylene blue. So they use this point on the left and a point on the right, and look, search for the equation of this point of this line, and then they subtracted all this from the spectrum. Okay, here are the way they did their calculations. You're going to have this presentation, so I won't bother with this. But this is how it looks. It looks beautiful. This is the baseline corrected 30 microliter spectrum of methylene blue obtained under source condition. As I mentioned before, integration over band intensities, what you do is that the areas under a band, or if the bands are close together, such as in here, okay, you don't try to do a single band. Just integrate over these two bands, okay? And that brings up the concept of Rayleigh's proposition to when are two bands resolved. And Rayleigh did not propose this proposition based on Raman spectra or infrared spectra. He used the proposition was in general terms. So follow with me. So you start here, go up, 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 down, 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 down. And when you're doing that going down, if the new band on the right starts to appearing, these two bands are not resolved. To be resolved, the band on the left should have gone this way. Look at the cursor. Okay? So whenever a second band comes in before the first band hits the baseline, you say that the bands are not resolved. I'll show you later on. But if the first band hits the baseline before the second band comes in, those two bands are well resolved. And they could be well resolved by a point, or one band could be placed in Maya West and the other could be placed in San Juan. Okay? There's the criterion is not how far they are separated, is if they are separated or not. So the integration means sum over the cells. And we're going to do a summation from 420 wave numbers all the way to 490 wave numbers. And this is what they found. They integrated, these students found for the integrated intensities for 1 microliter, for 2 microliters, 3, and so forth. And you get all the way to 30 and to 40, okay? This is the calculations for the concentrations. I won't bother with it. We're gonna have this presentation. Same here, but important. Definition of theta. Theta is equal to the intensity of the individual solution of the analyte divided by the intensity of the surface. So when you do SIRS, you better run the spectrum of your colloids before you run your spectra so that you can calculate theta, and that will eliminate fluorescence. That's the best way to eliminate the fluorescence, okay? It's unfortunate that I didn't do it for this experiment, which I did about 3 years ago using the Raman system, the small Raman system that we bought for the physical chemistry lab, which is in room 027 at your left when you immediately when you enter. So for 1 microliter, theta is equal to 0.02. And this is the beauty of Freundlich's model. You see, the heading on the graph, you don't place it on top of the graph. You place it in the graph. You make sure that you cover the x-axis and the y-axis completely or nearly completely. Here we went all the way down to minus 4.6. We could have gone a little bit better. That's okay. And on the right, we went to about minus 2.8, which is further than we should have gone. But look, this is the trend line for the absorption process using Freundlich's model. You can see that you can get a slight saturation points of 30 and 40. They're basically the same intensity, okay? And you have a little bit of scatter point. Not all the points lie on top of the trend line. But this is excellent. This is R square is 0.9862. That's 98.6% of R square, which is very good. Remember, Raman is not accurate more than about 10 to 15%. So these data points are very, very good. But they can be better, okay? And this is what I've done here, eliminating one data point. And you can see that just by eliminating one data point, the R squared went all the way up to 99.5%. And if we eliminate two data points, I'm in the big leagues, 99.7%. And the scattering of points is almost negligible. So this is, I didn't show you like mirror. I just wanted to represent this the best way possible. Here's the detection limit for the SIRS experiment. It says useful SIRS range is from about 15 micrograms per liter to 75 micrograms per liter. If the full range of the concentration is used, we would have gotten an R square of 92.4%. Since we use the lower part, 1 microliter, 2 microliters, 3 microliters, 4 microliters, 5 microliters, so the R square is 99.7%. Here are the references, and let's go to the Excel. Can you see this well? This is the Excel file. Can you see this well? Yes or no? Someone?
Yes.
You can see it?
Yes.
Okay. So what I'm gonna do is select from 440. Well, first of all, let me represent all the spectra. Lots of data points. For reasons that I don't understand, the CH region doesn't show up very well on SIRS spectra. So this has been cut to about 2,000 wave numbers. Okay. So we have selected the data, both the x-axis and all the y-axis. So we now go to insert, if I can find it. Okay, here's the insert. And we're going for charts. We like the scatter chart, but with continuous. And this is it. Beautiful. Okay. All right. Okay. So let's do magic with it. Okay. First of all, move the chart title in the graph. So I can eliminate the horizontal and vertical lines. Third, we tell Excel that we want to format the full chart area, and we go to border. We tell the program that we want a solid line. and we select the darkest possible color, and the width, I like 2.0, and there it is, okay? On the outside, I won't want to have anything, no borders on the outside. So no line. Regarding the fill, no fill. Okay? So you're gonna see the background, but we can change that later on. Regarding the oh yeah, okay, I see what happened. It didn't do the micro symbol. We're not gonna mess with that right now. Okay, you could use Calibri, but I'm biased with Arial. Let me go into Arial here. Okay, we'll tell it that that's going to be in bold Arial. Tell it that, but the point is not too big. So let's put that at 12 and very dark. There it is. Okay, remember, those are not milliliters, they are microliters. Okay, then the next thing is move this a little bit and change this to Arial 14. Very good. Okay. On the x-axis, again, change to Arial 14. Good. Okay, almost ready. Okay, the spectra cut off about 200 wave numbers. But let's add in uh, the uh, the tick marks. And we want the tick marks on the outside. You can't see them, and that's because I haven't added enough color. So let's put solid line, very black, and 0.2. Now you can see them. Okay, go back and select on axis options. Let's start with 200 wave numbers. There's no information below 200. Before you hit 200, sit on top the maximum. That's it. Okay, great. Okay, the maximum, it doesn't go all the way to 1800. So let's put that 1700. Okay, all right. And let's do the same with the y-axis. Where's the tick marks? Place them outside, label them very dark, with, again, 0.2, the width. Good. Okay. So we're almost ready to do chemistry. On the axis options, you see that the major axis for the y-axis, it shows as 5,000 counts, and the minor as 1,000 counts. You want the minor to be a half of the major. So we put 2,500 right there. And you have just one tick mark between two labeled tick marks. Let's do that the same for the x-axis. And let's put this 100. I like better 100. And the half of the 100 is 50. Don't worry, you can always put this bigger. That's beautiful. Okay, go back again to the y-axis. We have empty space here. First, let me fix this.
Yeah. Okay. Everybody. On the way.
Almost done. Very black and bold. Beautiful. Okay, so now we go to the y-axis and tell it that 20,000, 21,000 is better than 20. That's it. Okay. You see that we've overdone the x-axis, and that's very easy to fix. Not quite.
Okay.
I don't like it. But we'll mess with that later on. Okay, but okay. What's left? Labeling the x and y axis. So now you go to you're forgetting. So bear with me. Chart design. Add chart element. Axis title. Primary horizontal. That's there. Primary vertical. Okay, great. Let's fix the vertical axis first. All right. We're done with the label on the y-axis. Let's label the x-axis. And that's in Raman shift. Almost done. You'll have to look for the exponent and tell it it has to go higher. So you go into font and you tell it's a superscript. Voila. We're done. Okay? Okay, now for the integration of the bands, we want to integrate. Let me copy that. I'll show you what we're gonna do. Okay? Now we're going to select this band, these two bands only. So we tell it the y-axis should go from about 400 to about 590. Okay, all right, great. So we're going to integrate from, okay, let's change that before let's change that. Now we can go 50 to 25. We can go lower than that. 30 to 15. Okay, that's good. All right, so we're going to integrate from 400 all the way to about 580. So now we go to the data and we select all the columns and rows from 400 with numbers all the way to 580, 590 wave numbers. I did something wrong. I don't need the the x-axis. Let's start again. So go from here. To 590. So we call a function called intensity equals the sum of sum of what? B, and what? B220 all the way to B437. What happened? I don't know what I'm doing wrong. Let me do this quickly, just a second. Okay, now. That's it. Okay, I'm sorry about that. Okay, this is it. And I know what he did wrong. Copy. Okay. Let's see what happens. Now, okay, C, 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 okay, I'm gonna do this some other way. Okay. Okay, that's it. Okay. Here are the integrated intensities. This is all the way to M. This is it. Okay. Now I have the integrated intensities, and I want to plot them as a function of what? Of concentration. So, but I need to work more on that. So that you get the idea. Okay, I think we've done long enough now. We've been about an hour and 17 minutes. May I have your questions, please? Preguntas. Thank you, Mariam. How do I stop recording? Okay, good. Okay,